The Doppler effect, or Doppler shift, is the apparent change in frequency of a wave in relation to an observer moving relative to the wave source. The Doppler effect can be observed every day. A common example of Doppler shift is the change of pitch heard when a vehicle sounding a horn approaches and recedes from an observer. The reason for the Doppler effect is that when the source of the waves is moving towards the observer, each successive wave crest is emitted from a position closer to the observer than the crest of the previous wave. Therefore, each wave takes slightly less time to reach the observer than the previous wave. Conversely, if the source of waves is moving away from the observer, each wave is emitted from a position farther from the observer than the previous wave. So the arrival time between successive waves is increased, reducing the frequency. We can use this in our experiment to determine the energy used in each swing because of the conservation of energy. When a pendulum swings, potential energy is transformed into kinetic energy, and then back again to potential energy as the speed and elevation of the pendulum vary during the motion. In simple pendulum with no friction, mechanical energy is conserved. Total mechanical energy is a combination of kinetic energy and gravitational potential energy. As the pendulum swings back and forth, there's a constant exchange between kinetic energy and gravitational potential energy. When we originally hung the pendulum, there is no net energy. However, when we move to a pre-swinging position, we put in energy, which the pendulum converts to Ke, or kinetic energy, and then back to Pe, or potential energy. Our hypothesis for this experiment is that as the angle increases, the energy loss will also increase. In order to create a pendulum, we use the following: a meter stick with a hole at the top, lots of duct tape, a nail driven, 2 phones, one with Phyphox tone generator and one with Phyphox Doppler effect. At the end of the meter stick, we placed the tone generator phone and secured it tightly with duct tape, keeping in mind to do test swings after taping the phone to test its security before proceeding with the experiment. Once this is done, we then hung the apparatus on the nail, making sure to pad the space on the nail with duct tape to prevent it from wobbling as it swings. Then, we marked the places on each angle we were testing. To do this, we used simple trigonometry. If the length of the meter stick is 1 meter, meaning 100 centimeters, we can find the x value, or the horizontal length, using the length of the meter stick and the intended angle. For example, if we were testing 15 degrees, the 100 centimeters would be the hypotenuse side, while the x value would be the opposite. Thus, in our calculations, we can use sine 75 is equal to x over 100, with x being sine 75 times 100, for example. Like that, we would be able to find the horizontal values and mark those values on the wall with tape. The Doppler effect phone is also placed a certain distance away to avoid any noise cancellation. From this, we can then swing the pendulum marked from the marked point and letting it swing for a certain number of oscillations. We'll then be able to extract the data from there. Next, we calculated our theoretical curve. So, how did we get our theoretical curve? First of all, we used the 2 equations, Pe, or potential energy, and Ke, or kinetic energy. We know that in the context of conservation of energy, Pe will equal to Ke. Pe, potential energy, is equal to m, mass, times g, gravity, times h, height. Whereas Ke, the kinetic energy, is equal to 1/2 times m, the mass, times v squared, or velocity squared. When we set the 2 equations equal to each other, m will cancel out, resulting in gh equaling half v squared. From there, we can isolate v, or velocity, getting velocity is equal to 2gh all squared, or all rooted. So, when we plug in our values, we will get the following. V is equal to 9.8 times 2 times 1 minus cosine theta, which is all rooted. So how did we get 1 minus cosine theta? First of all, we know that our meter stick is 1 meter. So we had to find the length of the side of the triangle called x. Due to where the angle is, we would be able to use the cosine identity and get x is equal to cosine theta. From there, it would become 1 minus cosine theta, as it's the total length, or the total length of the meter stick 1, minus cosine theta, which is the value for x. And of course, we would use the positive square root, because we cannot use negative values. So the reason why it may seem like our theoretical curve is linear is because we're actually looking at a small specific portion of a graph, which makes it seem like it's linear when in reality it is not. And these are the results we collected. The data collected and processed was using Excel and Desmos included the inbuilt processes such as averaging, standard deviation, and graphing. Based on the comparisons of the expected velocity to the data collected, the hypothesis wasn't entirely supported, as the theoretical velocity for 15 degrees and 45 degrees, as well as 45 degrees, were outside of the experimental standard deviation. 15 degrees had an experimental velocity of 0.90 meters per second, with a standard deviation of 6.7%, which lies above the theoretical velocity of 0.82 meters per second. While the 40 degrees, which had an experimental velocity of 2.03 meters per second and a standard deviation of 2.82%, lies below the found theoretical velocity of 2.14 meters per second. This can be attributed to errors in the measurements, such as the assumption that air resistance could be treated as negligible in these calculations. As seen in the trials for 40 degrees, the pendulum spends more time swinging, causing it to experience more air resistance, which resulted in a lower experimental velocity compared to the expected theoretical velocity. Similarly, the trials for 15 degrees may be faced with higher starting points, causing there to be a higher velocity than the expected value. For 40 degrees, it was out of the error bar, because as the angle increases, it loses energy and the data points become sporadic. For 45 degrees, it's the same conclusions for 40 degrees. As the data point is still technically within the error bar, however, we still think that this data is wrong due to the standard deviation being incredibly high in this case. As for the 15 degrees, we believe that since this was one of the trials we did, and since it was the first trial for our entire experiment, we don't think we did this correctly and didn't have the time to replace it due to time issues.